Okay, so before you continue watching the video, I'd like you to try to um, go to the homework folder, go to the Unit 6 folder, and complete the handout L1 Prob Dist Intro, the Intro to Probability Distributions. You're going to get a chance to actually create a probability distribution for two simple experiments. Let me pull up the file. So this is what it looks like. So you can see you're going to record the probability of rolling a single die for each of the outcomes 1 through 6. And then once try to record it as a decimal. You can record it up to maybe 3 decimal places, or 2 decimal places is probably the best. And once you have it recorded as a probability to 2 decimal places, you're going to draw the bar graph over here on the grid. Record on the horizontal axis the outcomes, which in this case are 1 through 6. Your vertical axis is the probability of each outcome, and so record the probability for each outcome by drawing a bar. Now try not to have any thickness to the bar, just make it a single solid straight line that goes up to the appropriate probability for each outcome. There doesn't need to be a thickness to that. And once you're done that one, skip over number 2. We'll get to that, and then do the same thing for the second investigation, rolling 2 die. So again, record the probability of each outcome to a couple of decimal places. Notice I've got 1 here, but really that has a probability of 0, so 2 through 12. And then record the outcomes on your horizontal axis. Probability is your vertical, and again, draw bars to the appropriate heights for each outcome. Okay, so before you continue on with the video, try to do that on your own. Okay, hopefully you've had a chance to try that assignment on your own. So let's look at what the first investigation should look like. So I've already kind of completed this one. So the probability of each outcome is 1/6. 1/6 all the way down to 6 will be 1/6. And so then I express it as a decimal, so it's about 0.167 or 0.17 roughly. And so that's the probability. And then my bar graph, notice I've recorded the outcomes on my horizontal axis, and on my vertical axis these are the probabilities. So each bar needs to stretch to a height of about 0.167, so it's just slightly under 0.17. So you can see the probability of getting a 1, I've drawn a bar up to that height. For the 2, 3, 4, 5, and 6, the bars are the exact same height, so I've drawn bars up to 0.167. And again, notice that there's no thickness to the bars. They're just a solid line, and again, that's because this is the probability of exactly getting a 1. We don't want a thickness because it's exactly that discrete value, the probability of getting a 1. If we add any thickness to it, that implies that there's something beyond the 1. So if I made a bar that was around the 1, it would mean a little bit below 1 and a little bit above 1, and I don't want to imply that. So these are, as we'll learn, this is a discrete probability distribution that we've just created. Now let's look at what it would look like for the 2 die. Okay, so I've already gotten through most of the probabilities and the graph for the second investigation. So notice all the probabilities are listed. So for example, the probability of 2 turned out to be 1/36, which I recorded as a decimal, which is also the probability of 12. That outcome, again, 1 roll out of 36 possibilities. We've gone through that several times. It's got to be a 6 and a 6 to get, for example, 12, and for a 2, 1 and 1. Then for 3, it turned out to be 2 rolls out of 36 to get a 3, and the same thing for 11. For 4, it's 3 rolls out of 36, and again, those are 1 and 3, or 3 and 1, or 2 and 2. And the same thing for 10. Same thing, it's 3 out of 36. For 5, there's 4 ways of getting a 5 out of 36, and the same thing for 9. 4 ways of getting 30 out of 36. For 6, there are 5 ways out of 36 to roll a 6, as there are for 8. 5 ways out of 36, and the one with the highest probability is rolling a 7. There are 6 ways out of 36 to roll a 7. And then I started making my bar graph, and so what I'm doing is I'm just making it a little easier on myself, I'm cloning a whole bunch of lines, and so I'm up to the probability of 8, which is 0.139. So there's just underneath the 0.14, and I know that my probability of 6 is the exact same, so it's just easy if I clone that and just put that there, and I've got one more to do, which is the probability of getting a 7, which is 0.167, and there we have it, just underneath the 0.17, so say right about there. And so I've created the bar graph, which we'll find out this is the graphical version of the probability distribution for this investigation, for this experiment. We have on the left the table of values. We call that the tabular form, and on the right we call that the graphical form of the probability distribution, which is a distribution that shows you the way all of the probabilities are distributed for this particular experiment, which is rolling 2 die. Now notice that they look visually very different. For a single die, all of the heights of the probabilities are exactly the same, 0.167, and this has a special name that we'll find out a little later. And this one rises up to the middle and then goes down at the end, so this kind of is symmetrical, looks the same on the left and right. And again, this one has a special name, and we'll also investigate that and talk about that a little later. So there's our kind of graphs for this. Let's continue on. So notice in the investigation there is a part where I ask you to calculate the expected value. Now, expected value is an important concept in probability theory. An expected value, and when I talk about it in class, I want you to think of the long-term average. We're going to talk about how to calculate it, but then I'm going to talk about what exactly it means. So here's the definition of it. It's the predicted average of all the possible outcomes of a probability experiment. The expectation, or the expected value, the way we calculate it, is equal to the sum of the products of each outcome with its probability. So notice we have some special notation down here. So this means the expected value of x, where x is some sort of variable, a random variable. So it could be, for example, in our roll of a single die, x is either 1, 2, 3, 4, 5, or 6. So it's a variable. It takes on various values, but it's a variable that takes on values that are random. So in our example of a die, 1 through 6. Now on the right hand side of the equation, we can see we are going to find the sum of each outcome, x, multiplied by its probability, and we're going to add those all up. So we're going to see how to calculate the expected value of each of those two experiments we just did. Okay, so here we go. How do we calculate the expected value? It's a pretty simple calculation. We're going to multiply every outcome by its corresponding probability. Now for this, I'm going to convert each one back to its fraction form, and you'll see why that is. It just makes it a lot easier to calculate the expected value. Once we've multiplied every outcome by its probability, we're going to add up all of those products, all of those multiplication answers. That will be the expected value. The sum of that will be the expected value. Now here's something we want to remember as we move through this unit. By definition, when we talk about a fair game, its expected value is 0. Anything that is different from 0 means it favors one outcome or another. So it might, if in a game, for example, it might favor one player versus the other player. So we're going to go back to the handout. If you think you know what you're doing, you can try to calculate the expected value for each one following this model. But if you want to go on and check the next minute or so of how I calculate the expected value for the single die, you can watch that and then try the 2 die example on your own. But try to do it on your own and then continue watching. Okay, so I'm going to show you how to do it for the single die here, and either hopefully you've tried it on your own, or if you just wanted to see how to do it for this one and then try the next one on your own, that's fine too. So notice I've written all the probabilities out again, and notice I've written them out as a fraction this time. For the purposes of making the graph before, it was easier for me to have the decimal so I could plot the bar graphs accurately. But here, since I'm going to do some calculations, it kind of becomes laborious to use those decimals, so I'm going to go back to the fraction form. Now, to calculate the expected value, value, so I'm going to be doing the expected value in this column. Okay, I'm going to multiply each outcome by its corresponding probability. So 1 times 1/6 is 1/6. 2 times 1/6, 2/6. Notice I'm not going to reduce this, and there's a good reason why. 3 times 1/6, 3/6, 4/6, 5/6, and lastly 6/6 for 6 times 1/6. So I've multiplied all the outcomes by their corresponding probabilities. The next part is to find the sum of this column, because this is x times p of x. I multiplied all the outcomes by their corresponding probabilities, and that's this column. So now I need to add those all up, and you can see why I didn't reduce it, because now they've all got common denominators. Makes it a lot easier to add. So I'm going to add 6 and 5, 11, 15 plus 3, 18 plus 2, 20 plus 20 plus 1 is 21 over 6, which is approximately, well, it isn't approximately, it's exactly 3.5, and there it is. That's the expected value. So the expected value of this experiment, rolling a single die, is 3.5. Now what does that mean? What that means is if I rolled a die a lot, so let's just say 1,000,000 times, and I recorded the outcome of that die 1,000,000 times, the average roll, okay, so adding up all the rolls and dividing by how many how many times I rolled, would come close to 3.5. Here's a further illustration of what expected value means. So I'm going to create a random integer from 1 to 6, just like our die, and I'm going to create, let's say, 1,000 random integers from 1 to 6. So in essence, I'm rolling my die 1,000 times. There it is. So I've created a column with 1,000 numbers randomly generated from 1 to 6. Now, if I want to find the mean of that column, I'm going to go to my next row, and I'm going to calculate the mean of that column. So mean of the die column. Now, the calculator is going to try to give me the exact value. Let's see what it gives me. 433 over 25. Now I'm going to ask the calculator to try to give me the approximate value of that. So I'm going to go back in here and ask it to do the approximate. By approximate I mean change it into a decimal. Okay, and here we go. And there you can see the answer is 3.464. I'm going to increase the trials a little higher. I'm going to make them 2,000 trials. So in other words, imagine rolling a die 2,000 times. Watch the average. It's going to overwrite the old data. 3.539. It's getting even closer to that expected value that we calculated, 3.5. If I go just a little higher, the highest that I can go is 2,500. That's the list length for this spreadsheet, and here we go. I'm going to overwrite 3.4992. So as you can see, the more rolls I have, the average roll is 3.5. And I know I'm not going to roll to 3.5, but that's what expected value means. It's the average long run roll, long term roll, if I roll a die a lot of times. Let's try to see what we'd get for 2 die. Okay, I've completed most of the expected value calculations here. So notice again, I wrote out the probabilities for all of the rolls, but out of 36, and again I didn't reduce them. And then I've multiplied every outcome by its corresponding probability. Okay, and this is my expected value column. Okay, that's over here. So I've multiplied all those. I have one more to do. 12 times 1 over 36 is 1236. Now again, I need to find the sum of this column. So I'm going to pause here and calculate. Okay, so now I need to add up this column. So the expected value will be the sum of that last column, which is 252 over 36. So again, I didn't reduce my answers here so I could have that common denominator, and when I find the divide that works out to 7. So again, what that means is that's the long-term average. I'm going to need to pause here because I need to upload the video, and I'll put part 2 with the rest of the lesson.